Hi, welcome to this second video. In this video, we're going to learn about some statistics terms, and we're going to learn also about the Gumbel and normal probability distributions. So we have four problems for this this section of the book, um, and we're going to solve problem 2.1, 2.4, 2.5, and 2.9. I have set them up in a way so I can, it's easy for uh, all of us to understand what the problem is asking us. And also it's gonna be easy to understand some new terms. Um, let's start with the problem 2.1. Uh, this problem, as I've mentioned in the previous video, I have reworded the problem so it makes a little, it's more clear, makes more sense, and it also gives me the opportunity to explain new concepts. So let's start. 2.1, we have 25 years of hydrologic data and want to estimate the magnitude of a 10-year return period event, which is a flood that statistically has a 10% chance of occurring in any given year. Considering this 25-year dataset, what is the likelihood or reliability that our estimate of the 10-year event will be within plus or minus 25% of the actual value? That's part A. Part B, how much data, record length, would you ideally need to reduce the margin of error to zero when estimating a 10-year flood event and be 100% reliable? Uh, for this question, the table doesn't show a 0% error, so we're gonna use the plus or minus 25%, and that actually matches with the actual answer that the book gives. An important note, it's not possible to achieve 100% perfect accuracy in hydrology. There will always be some level of uncertainty in flood predictions. This is in engineering, we are used to getting actual numbers but in hydrology, all we can do is get close to it, and there is always going to be some error or in our calculations. Um, so to solve this problem, all we need to do is use this table 2.5 offered in the book. And I'm going to use this problem to explain two concepts. The first one is confidence limit that the table uses over here. I found that a video that if you watch it is 4 minutes long. It's called, you understand pretty well what these terms means if you're having problems understanding the concept behind it. It's understanding confidence intervals, statistics help by Dr. Nick. You can find it on YouTube. And I also want to explain what return period is. This is a concept that took me a while to understand, and I feel like the reason why it took me so long is because I never could find someone uh, who can explain it as clear as it needed to be. So I found that using a an example or a like this one here, we can understand what it is. So let's use this example of a 25-year return period. It says, think of a bucket with one red ball, which represents the event, and 24 white balls representing no event. So 1 and 24 is going to be 25, so that represents 25-year return period. In this example, you draw a ball blindly every year and then put it back. The chance of drawing a red ball, the event, remains 1 over 25 or 0.04 or 4% chance in each independent draw or year, regardless of the previous draw. So what does this mean? If we go to these examples that I have here, the 2-year return period says is 1 in 2 years or 50% chance of drawing a red ball or having the event. Uh, I hope this helps to understand. But a 2-year return period, all it means is that you have each year you have a 50% chance of having this event, or it could be a flood, or it could be a drought. a 10-year return period only means that is that you have 10% chance of drawing a red ball, of having that event in that year, and so forth. So a 500-year return period, what it means is you have 0.2% chance of having that event that year. So each of these represent the percentage of chances that you have to draw a red ball. So a misconception is that if we say, oh, this event is a 2-year return period, that means it happens every 2 years. The reason why this is wrong is because if you have a bucket and in this bucket you have two balls, one red and one white, if you, in your first try, representing the first year, you try to get a ball, you might get the white ball, which means not event. And if you try again, you put that ball back, right? And if you try again, you might again get the white ball. So there is a 50-50 chance that you will get the red ball. So it won't happen every 2 years, but the chances that it will happen are pretty big because there are only two options. So in a 10-year return period, you will have one red ball, which means the event, and nine white balls. So the chances that if you get you try to draw a ball from the bucket, the chances that you pick the red ball are much smaller. They're lower. So it's not that the event is gonna happen every 10 years, but your chances are 10%. You get 10% chances. Uh, I hope this clarifies a little bit the idea of what a return period is. This is a very, very simplified example, and I feel like it will help you understand better what a return period is. Um, I have a note here at the bottom that says, notice that the greater the return period, 500 years is the greatest that I have, the smaller the chances of the event happening. That means that the most rare events are related to low chances, or in other words, high return periods. The worst event is the worse the event, the less likely to happen. Um, so let's move on to the questions of this program 2.1. Table 2.5 shows return periods, record lengths, and confidence limit. So for part A of the question is asking what is the likelihood or reliability. All these values here represent the reliability in percentage. The table doesn't show it, I would say, very well, but you can tell by the title. All these values here are the reliability. So if we go for a 10-year return period, would be this section here, and plus or minus 25. So that would be about here for a 25 record length. So it would be 25 record length plus or minus. So the answer will be 93%. And part B, we have how much record length or data do we need to be 100% reliable in a 10-year flood or return period. So if we consider the plus or minus 25%, if we want to get 100% reliability, quotation marks, because you're never gonna get 100%. You will need a record length of 100 years. And those are the answers for this question. Now, problem 2.4. In this problem, we're gonna understand or get more familiar with the Gumbel distribution equation. The problem says, imagine a smaller river flowing into the Delaware River. We believe a specific statistical method, the Gumbel distribution, fits best to the area and can help us predict future floods in this smaller river. Based on past data, the average peak flood is 4,000 cubic meters per second, and the data shows some variation, standard deviation of 600 cubic meters per second. If a flood has a 1 in 20 chance of happening each year, or in other words, a 20-year recurrence interval or a 20-year return period. These are different ways to say the same thing. How big do you think the flood will be in cubic meters per second? So they're already telling us that uh, the the flood in this river fits the Gumbel distribution equation. The Gumbel distribution. So we're gonna use the Gumbel distribution equation, which it's in the book, and this is what the book tells us. Um, to solve this problem, we actually don't need to solve for all of this because all it's asking us is for the magnitude of the flood rate, which is x. So we're gonna have to use the b section. There is a b here. I don't know if you can see it. It's pretty small as part of the equation. But here they show us what b represents. And I put it down here. Um, this is the equation to solve for b. So to solve for b, we're going to need all these values here. The average, the standard deviation, the return period, and a value of b. And the way we get the value of b is from table 2.3 that I got it here. This is also from the book. Before we solve for this, I want to explain a little bit what that b represents in the Gumbel distribution equation. You don't have to be a master on this, but I feel like it's gonna be just good for you to understand a little bit what it represents. So the Gumbel distribution, the parameter b represents the scale parameter. In terms of its shape, it controls the shape or spread of the distribution. Um, what it means is like it's gonna make it a peak higher. This is an example of the Gumbel distribution here on my right. It's gonna make it either higher or flatter, like no as high. So the b value controls that part. Actually, I think it explains here the magnitude. The magnitude of a larger b value means the distribution is more spread out or it's flatter, while a smaller b value means it's more concentrated, peaked. What I was saying. The units of the b value. The scale parameter b has the same units as the variable being modeled. For example, if the Gumbel distribution is used to model rainfall, and rainfall is measured in inches, then B will also be in inches. So in our case, we have the values of cubic meters per second. So our B value also will have that unit. In essence, B determines how wide or narrow the distribution is. A larger B means a greater chance of observing extreme values, while a smaller B means most values will be closer to the average. So now let's move on and try to solve this problem. So according to solve for, if we use the b equation, we want to know how big the flood will be. So we need to know the magnitude of the flood, which is x in the b equation. So this is the b equation. Solving for x, we get this. So we need values for the standard deviation, b that we'll find in the table, and the average, which will be x bar. So having a return period of 20 years right here, the b value will be 2.970. 2.97. And now having all these values, now we just need to plug in and we'll find the answer. Times s times b plus x bar minus 0.45 times standard deviation again. And this is in cubic meters per second. So this is the answer for this problem. Now, this was the Gumbel distribution equation. Let's move on to the next problem that will help us understand the binomial distribution. And the way the book words this problem is very, very confusing. So I hope this version is simpler. 2.5. We are interested in severe droughts. Let's say a 50-year drought is a drought so severe it statistically only occurs once every 50 years. If we track droughts over a 100-year period, what is the probability of encountering only one drought that's even more severe than this 50-year drought? So whenever we have a problem like that where we are comparing two values, uh, we can use the binomial distribution. And by using the binomial distribution, we'll get the probability, which is would be the answer to this question, since that's what is we're being asked. So according to the problem, we know we're being asked for only one occurrence and in a time range of 100-year period. So we're comparing it to a return period of 50 years, which will make our probability of one occurrence 1 over 50 or 0.02. Now, having all these values, we need to plot them or plug in into this equation. Now, this parenthesis of nx, it's this part right here. So this will be the equation, the complete equation, plugging this section into the main one, the main equation. So I think to get this right, I think we should solve by parts. So the first part of this equation is n factorial, which in our case is 100 years. So in Excel, you do fact, that will be the equation for factorial, n, and that's the number, then factorial of x, which are the occurrences. This is gonna be just, which is just gonna be 1, but let's do it. Now the next, n minus x factorial. This is gonna be equals factorial of n minus x. Get a number. Now p to the x is going to be equal to the probability 0.02 to the x, which is all 1, so it's going to be the same value. And then the last part, 1 minus p to the n minus x. So let's do 1 minus the probability of one occurrence to the n minus x, which will be 99, right? Minus x. Okay, we got all the values. Now let's plug in here. Let's do equal. Hopefully I get this right. Let's use parentheses. N factorial is gonna be this value over x factorial, which is 1, times n minus x that we have here, and then close that parenthesis and multiply by the other second part of the equation, which is p to the x, p to the x, okay, this part times the second part of the other half. So this is the answer. The probability of only one drought being more severe than this 50-year drought in a 100-year period is 27.07%. And this is how we work with the binomial distribution equation. Now, the next problem, this is mostly to get us familiar with statistics like the average, standard deviation, and skewness, which Excel is very good at this. It makes our lives easier. But we're being asked a lot of questions, a lot of this. Well, we're being asked many things in this problem. So let's go. Let's start by reading the problem statement. 2.9. We have data on the amount of rain in millimeters that fell in Scranton, Pennsylvania, each year between 1950 and 1985. The data I have it here. These are all the values as they're shown in the book, by the way. To understand Scranton's historical rainfall patterns, let's create a visual representation called a histogram that shows how much rain fell in different years. Create this histogram for the entire dataset from 1950 to 1985. That will be our first step. Next, we'll delve deeper by calculating some descriptive statistics. Find the average rainfall amount, which tells us the typical amount of rain Scranton receives each year. Also, calculate the standard deviation, which indicates how much the actual rainfall amounts varied in comparison to the average in different years. Finally, calculate the skewness, which reveals any asymmetry in the rainfall distribution. Were there more years with the lower or higher rainfall? That's what the skewness will tell us. We'll repeat these last three calculations for a modified dataset that excludes the first 5 years of data, 1950 through 1954. By comparing the results from the complete data with the data missing the initial 5 years, we can explore how missing data might affect our understanding of Scranton's rainfall patterns. So let's start with the histogram. Let's select all the data. We're gonna use the complete data set for this histogram. And we should insert a chart and we should pick histogram. I believe it's down here, histogram chart. And let's divide it in six. This divided by six. Let's divide it in 100 units. So let's see how we can do this. Customize ISM series. Bucket size here. So there is no 100 option, but I believe we can type it. Yep. So we got the histogram right there. Now series. Let's horizontal axis. Okay, let's do some titles. Horizontal axis. So this actually will be the occurrences. Oh, these are the occurrences. Okay. Says, and the horizontal one is going to be the millimeters of annual rainfall. And short title, this is for Scranton. Okay, I think this is good for the first part. Um, Now that we're done with the first part, let's calculate the average for the complete data set. So let's do average of the complete data set will be all the way down. Standard deviation, again, and skewness. Make sure you use the first one and not the skew.p because this is for populations and this is for data sets. So usually in hydrology, you don't work with populations. So you usually work with recorded data, like in this case. So this will be the skewness. Now that's the second part. Now let's do the same for the last part, the incomplete data set. Average. And this one is gonna be 1950, 1954. So starting from 1955. Let's do standard deviation. Again, starting from 1955. And same thing with the skewness. So the values do change, and we see that, and I assume this is obviously more accurate because we have more values. So in hydrology, the more data you have, the more accurate. You're never gonna be 100% accurate, but um, the reliability is higher. And I believe this is the last problem for this section. And to let's review. So with the first problem, we um, learn about confidence limit, return periods, and how to use table 2.5 uh, to for a relationship between confidence limits, how much data you have, depending on the return period you're interested in. And the second problem got us familiar with the Gumbel distribution and how to use it to find um, the flood of a specific river, given that you have data that where you can find the average standard deviation and for a specific return period you're interested. Which, to be honest, is pretty cool that you can find a specific value amount if you can have all the data from one equation. And the binomial distribution, again, comparing two values, you can find a probability. Um, and for the last program, it was pretty simple, is to make us familiar with the with histograms and how this can be visually explain a little bit that um, how how a specific area is represented. Um, in this graph, we can see that there are more values. It's skewed to the it's negative, so it means there are more values above average. Um, and I feel like it's very useful to give us a rough idea. When just we just have numbers, uh, it's hard to see those things, but with a histogram, you're gonna use it a lot, especially in hydrology, to get a representation of your data. So yeah, I hope this you found this helpful, and I'll see you in the next video.